So, good evening, everybody. Duncan and I are going to tell you about some exciting work that's been going on to bring Shelley to the Cardano blockchain. This is work that's been going on, as many of you know, for an extended period of time. It's work that's involved a great many people. So, we're representing here many of our colleagues in various teams of the formal methods team, the Haskell engineers, but also quality assurance, the communications documentation teams, etc., etc. So, what is Shelley and why is it important? Well, Shelley brings a number of key features into the Cardano universe, and in particular, it brings the concepts of staking and delegation, where you can effectively lend your ADA to block producers. It brings the concept of earning rewards. It has decentralized block production, so it takes us much closer to the idea of a fully decentralized financial instrument that Charles was describing earlier. It also brings a number of important commercial features, including the ability to have multiple signatures on transactions, and also to embed transactions with metadata. And in addition to that, there are many, many improvements under the hood, including a new consensus protocol based on Ouroboros Preus, Sybil protection using pledging, pool metadata aggregation so that stake pools can advertise their identity and preserve their identity in a sensible way, etc., etc. So how did we get here? Well, the road to Shelley has been a long one, as I said, but recently we've been moving very fast down this road. So we started off with the Byron SL implementation, which has been running on Cardano for an extended period of time. And recently in March, we released the Byron reboot implementation, a complete new implementation of the Byron era ledger and consensus rules, but written in Haskell. So using BFT consensus, Byron ledger, plus various other features. We're now about to go through a hard fork, and this hard fork is going to move us out of the Byron era and into the Shelley era. And in the Shelley era, we'll have all the features I described to you before, decentralized block production, etc. But we'll also have these important new internal features, a new consensus mechanism based on Preus, new ledger rules based on Shelley, extended CLI, database functionality, client API, transaction metadata, etc., etc. So the Byron reboot, as I said, it's important because it's a complete rewrite of the original Byron SL code base in Haskell, a purely functional language that you'll have heard a lot about during this conference, using a new formal methods approach that our Director of Formal Methods, Philip Kant, will be telling you about tomorrow, but also using an easily extended and modular design that means that we are going to be able to very quickly and easily bring in new features in the future. So we think it's an incredibly important feature of the new implementation that because it's modular, because it's easily extended, we will quickly be able to bring you features like smart contracts, etc. It's also, as I hope many of you know, is much faster and, as our DevOps will tell you, much more reliable than previous code base. And this is great because the Shelley implementation is based largely on the Haskell Byron reboot code base. So what's involved in Cardano? Just to give you a peek under the hood, and Duncan will tell you a bit more about this tomorrow, but the node is the center of a complex ecosystem of components that collectively deliver the high quality Cardano experience that we expect. The node is comprised of a number of components. The two most important components are the ledger mechanism that tracks the movement of ADA through the system, and the consensus mechanism that makes sure that the nodes in the system synchronize properly and collectively work correctly to produce the blockchain, the Cardano blockchain. But in addition, we have the wallet backend, we have the Smash metadata server, we have the dataless GUI wallet, we have synchronization, database synchronization that feeds into these components, and many, many other things. So it's not just the node, it's not just dataless, there's much more under the skin here. So what have we done with the new Cardano node? Well, we've delivered the Byron reboot. We have produced a formal specification of the Shelley ledger rules, and from this we've produced an executable specification in Haskell that corresponds provably to the ledger rules, or demonstrably to the ledger rules. We've produced a key piece of technology, something nobody's ever done before, in the form of the hard fork Combinator. We're incredibly proud of this. We're so proud that Edsco, who has been working very hard on this over the last several months, will be telling you all about it in his own talk tomorrow. And we've also delivered various network improvements, performance improvements, a completely new database schema that builds on and extends the existing Byron schema, allowing the Explorer and other tools to deal with Shelley-era transactions in addition to Byron-era transactions. A new command line interface to allow people to interface and interact with the node, plus new cryptographical primitives that will greatly extend the security and integrity of the Cardano system. So this is a major endeavor. And I counted it the other day, and I figured that in total we have 1,753 Haskell source files. This includes all the tests, and tests are incredibly important to us. And in total, 330,000 lines of code, which, given this Haskell code, is incredibly impressive. You can think of that as being roughly equivalent to maybe a 3 million line C program or something of that size. So it gives you a measure of the complexity of the system that we've developed. The dataless GUI wallet, many of you will be familiar with because we've prototyped most of the new features in the ITN. And what we were doing is to bring those developments over to Haskell. We'll be deploying them on the mainnet in the very near future. And the main new features are delegation of stake, including ranking of pools using something called the non-myopic utility function, rewards accounts, wallet import, and many, many other features. So what are we trying to do here? What we're fundamentally trying to do is to build a distributed blockchain. And the way we're doing this is using a proof of stake mechanism. Charles has mentioned this. The idea is that stake is collected into a number of pools. Each of the stake pools runs a node, and these nodes extend the blockchain, forming a worldwide distributed network of block-producing entities that will collectively extend the Cardano blockchain under the agreed consensus. And the pools are selected to produce the blocks in rough proportion to the ADA that they hold. This is the proof of stake concept. The pools are selected to be slot leaders, and the slot leaders are going to produce blocks. But very importantly, only the leader knows it's been selected. Duncan's going to tell us a bit more about that later on. But one of the key security principles in the Ouroboros Preyas consensus protocol is that you cannot predetermine who is going to be the block producer and therefore attack that entity and bring the chain down. And the probability of election is also proportional to the stake. So the diagram on the right, I think, is quite nice. The little figure here on the right, it shows the geographical distribution of the first Haskell Shelley testnet stake pools. This was on the 12th of May 2020, and as I'm sure you will remember, we started the Pioneer testnet on the 11th of May this year. So already within the first day of operation, we had gone global. We had a distributed network of block producing nodes. I think it's incredibly impressive. Less than 1 day to a distributed blockchain. Great work, guys. So how does this block production work? Well, we've got a network. Here I've just got 5 nodes, but in reality, unlike blockchain, we're going to have many more than 5 nodes producing blocks. This is just for illustration. And say I've got 1 node that has 4 million ADA stake, 2 nodes that have 2 million ADA stake. The ones on the left are the red one and the blue one, plus a couple of 1 million ADA stakes. So what's going to happen? Well, one of these nodes is going to be selected randomly to be the block leader. Here is the one in the bottom left, one of the 2 million ADA nodes, and that is going to produce the candidate block for the upcoming slot. In the next slot, another leader is going to be chosen. Here is the 4 million ADA node. This is obviously has a greater probability of being selected than the 2 million one, but it won't be selected all the time. In the next slot, maybe it's selected again. So slot 2 it was selected, slot 3 it was selected. It's been selected twice as often as the 2 million ADA node, but not in a predictable way. And then maybe in the next slot, one of the 1 million ADA nodes gets the chance, because it has a non-zero probability of being selected. It has a lower probability, but not a zero probability of being selected compared with the other ones. It gets its fair chance of producing blocks. And in the next slot, maybe the other 2 million ADA node is selected. And you can see that over 5 slots, then the 4 million ADA node has been selected twice, the 2 million ADA nodes have been selected once each, and one of the 1 million ADA nodes has been selected. So what we've ended up with is a distribution of block producing nodes that roughly corresponds to the amount of ADA that each of them hold. And that is the principle of proof by stake. Block production according to the relative amount of stake that each of the pools holds. So how do we do this? Because clearly, we're not going to have millions of stake pools running, but there are millions of ADA or billions of ADA that are present in the system. Well, how we do that is by providing rewards to pools that are well performing in proportion to their ADA holdings. And the rewards we're giving, these are for producing the blocks and for maintaining the network. So basically for being good citizens, keeping the blockchain going. And they obtain their ADA from third-party delegators, normal people, people like you and me who maybe can't run our own stake pools, or maybe find that we don't have the time to run our own stake pools, or don't have enough ADA to make a difference individually. But by delegating our ADA to people who are willing to put that time and effort in, they can maintain the Cardano blockchain on our behalf. And in return, what's going to happen is that we are going to earn rewards from them. Now, of course, it isn't fair to let people do all the work and not give them something back. So, of course, the stake pools are allowed to deduct part of the something to cover their expenses, and we allow them to deduct the cost of operation plus some percentage fee, which, as we found on the incentivized testnet, is typically fairly small, but it's there to give an additional income to the pool operators to allow them to cover their operational costs, and so we can have a proper, well-functioning Cardano blockchain, because that's how we're all going to make this a success in the long term. So an operator, shown here in green, runs the pool. The operator needs some technical knowledge, but there may be multiple owners for a stake pool in the Shelley system. So how does that work? Well, the operator runs the pool. The owners pledge some of their stake to the pool, and pledging is a more serious action than simply delegating. It's a long-term commitment to the pool. And in return, what happens is the operator receives rewards for running the pool, as we've described, and then distributes them amongst the pool owners. So the pool owners obtain a share of the rewards, typically better than they would simply by delegating. And this is used, as we'll see a bit later, to improve the reliability and robustness of the network. There's no specific mechanism for how the rewards are going to be distributed to the owners. Everyone has to agree on it. The operator has to agree with the owners how each of them should receive their ADA rewards. They have to trust the operator, but the operator also has to trust the owners to honour the pledge that they've committed to. So the pool owners, they pledge some stake to the pools, and in total they delegate a specific amount to the pool to help it run. The pledge increases the rewards that a pool gets over and above the average, and by doing this it makes the pool more attractive to third-party delegators. And what that does in turn is to give some protection against Sybil attacks by requiring an attacker to own significant stake to be able to launch what we call a 51% attack against the Cardano network. You can also, of course, increase your pledge. So if you were to see an attack developing, the honest pool operators, who will be by far and away in the majority, can react to this by increasing their own pledge, attracting more delegation to their pools. And so we end up with an honest, well-run, efficient network. I mentioned trust before. A key aspect of the pledge mechanism is that the owners must meet the pledge that they've set out. If they don't do that, nobody gets any rewards. None of the other owners, not the pool operator, none of the delegators. As you can imagine, that's going to severely tick people off. So owners have to be honest, trustworthy people. They have to be people that the pool operator can trust implicitly because their reputation depends on the owners. At the end of the epoch, we give the rewards. The rewards calculation consider a number of factors related to the network performance, including the performance of the pool, how well the network as a whole has performed, something called the saturation limit, and the pool pledge. And there's a simple little formula that we use to calculate this. Don't worry if you don't understand it. It's all been worked out in great detail by Duncan, by Lars, by Philip, and by other people. And it's calculated very carefully to deliver sensible rewards whilst making sure the pledge has some influence on the reward level, the desired influence on the reward level. So what happens during a typical cycle is this. In Epoch 1, the pool will register. It needs to do this before the epoch end, before a window before the epoch end. In Epoch 2, it is registered on chain, and now it's eligible to be staked to. Meanwhile, in Epoch 1 or Epoch 2, a user, or even before, a user will register their stake key. In the next epoch, they can now delegate to the pool that's been registered. The delegation is active from Epoch 4 onwards. I've coloured this in blue. So the first epoch is coloured in blue. The delegation is active. The pool produces the blocks for the delegation. At the start of the epoch, we take a snapshot. And at the end of the epoch, we provide rewards we calculate the rewards for Epoch 4 in Epoch 5, and we deliver them in Epoch 6. And then in Epoch 5, we do the same thing, assuming the delegator doesn't remove their stake, they choose not to redelegate. We take another snapshot, the pool produces blocks, again according to the stake. The rewards are calculated for that in epoch 6. And in epoch 6, we take the red snapshot, we produce blocks according to the red stake, and so on and so forth. So I mentioned the saturation limit a couple of times. Now, this is an incredibly important parameter to ensure the healthy operation of the network by making sure there are enough pools in the system that can produce blocks, whilst making sure that the pools simultaneously receive enough rewards to be profitable so that we have a good, well-functioning system. So the idea is that if there's a target number of stake pools, and if a pool has more than its fair share of stake, it becomes saturated, at which point the rewards that it receives are reduced. So in the diagram on the right, the pools below the threshold in the dark blue, they're unsaturated, and as they reach the threshold, they become more and more saturated. So the pale blue pools up at the top, these are very heavily saturated, and they will receive proportionately less rewards than the other pools. So what that does is two things. It incentivizes owners to create new pools so they get the maximum amount of rewards, and incentivizes delegators to move their delegation to other unsaturated pools, and therefore to increase the number of pools in the blockchain. So to distribute the block production amongst more entities. So it's one of the key mechanisms that means that we will have a distributed blockchain. And in the theoretical limit, what will happen is there will be k block stake pools, all of which will have the same delegation and all of which will be saturated. But that's a theoretical situation. It's very unlikely that we will ever see that in practice. In practice, pools will be bobbing about above and below the saturation threshold, roughly there, and we'll see many more pools than simply the number k. So what have we chosen for k? Well, initially we're going to set it to 150. That's to balance the initial distribution of pools against the initial rewards, to make sure that we can provide sufficient rewards to get things up and running, but also to have sufficient distribution. And what we found on the incentivized testnet, that when we set k to 100, we could support about 225 or thereabouts active stake pools. So 150, it's a target number, but the actual number of operational pools we expect is going to be quite a bit more than that. And then we're going to increase this to 175 and so on and so forth. And thinking ahead, we're thinking, well, once we've increased it to 500, we should have about 1,000 stake pools operational, which was our technical target. And we will do this in such a way that the stake pools are viable, that there are enough rewards to go around these stake pools. That's the goal. So the pledge, I said, influences the rewards. It can influence the rewards by a greater or lesser extent. Higher settings give better Sybil protection, but we have to balance this against the pool operation costs to get the right balance, the right economic balance. So in the initial setting, we're proposing to set the influence factor to 0.3 initially. And if you look at the chart on the right, this little diagram on the right, what I'm showing you is the effect of the Sybil protection varying from 0.8 down to 0.1 for varying pledge levels. And what you can see is the level of protection decreases as the Sybil protection the influence factor declines, but it's still present even at very low levels of influence factor. So what that means is that even a setting like 0.3 will be effective in theoretical attack situations. The pledge factor and other things are also used in the pool ranking calculations that the wallet displays to allow users to choose their pools. So the non-myopic utility, which is based on game theory, the idea is that what is good for the network is also good for the delegator in the long term. In the short term, delegators might do better, but by playing the game, by abiding by the rules, in the long term, the delegators win, the pool operators win, Cardano as a whole wins. So what we do is we rank pools by desirability, which basically is a metric that tells you how well behaved a pool is, how much of a good citizen a pool is. And roughly speaking, you can say, if you look at this little formula down here, that the desirability is the rewards a pool gives minus its costs, multiplied by the return that it's going to give back to the delegator, so minus the percentage that it's taking as its own cut. And higher ranked pools are more attractive to delegators, linked directly to the rewards calculations. So everything is in balance. Rewards are in balance, pool ranking is in balance, delegators are motivated to do the right thing, pool operators are motivated to attract delegators, pool operators are motivated to protect the system to make it work well. So it's a really nice balanced system that's been devised here. So let me hand over to Duncan now and let him tell us about some of the technical details of the system. Duncan.
Thanks very much, Kevin. Okay, so I'm going to talk about the hard fork combinator very briefly. I would also advertise again, as Kevin did, that EDSCO, my colleague EDSCO, will be giving a talk on this topic in a lot more detail tomorrow. So if this piques your interest, then do pay attention to his talk. So what is the hard fork combinator? Let's just start with the terminology, which is frankly a bit silly. I mean, a hard fork is a piece of terminology that we inherit from Bitcoin, and as I say, it's not really a great term, because the whole point of what we're trying to do here is to avoid a fork in the network. We're trying to avoid the community, the whole system forking between two different groups. So people talk about hard forks like Bitcoin and Bitcoin Cash. We're trying to exactly avoid that kind of situation by having an orderly transition from one protocol to another protocol. So what is the hard fork combinator? Right, putting aside stupid terminology that we've inherited, what is it? It's a pretty impressive piece of technology that we've developed, which lets us move smoothly from one protocol to another. And that is actually much harder than it might sound on the surface. I mean, for starters, none of this gets covered in papers. When people write a paper about some awesome new blockchain protocol, they just assume that you're starting the world from that new protocol. They don't assume that, oh, you have to, you were in one and now you've got to somehow move to the other, and how do you match these things up? And that's all very difficult. And yeah, it is actually very difficult, because you have to do chain selection, across these boundaries. And what does that mean? You have to know what time it is. Proof of stake protocols are based on time. Ouroboros is based on knowing, what is the current time in a slot number. But that very notion of time starts to sort of shift underneath your feet as you start to do these transitions between protocols, because the slot length changes. And yet you don't know when the slot length is going to change, because when it is going to change depends on something on the chain, depends on when the protocol update proposal goes in to cause the change. So it turns out that you end up not even necessarily knowing a priori like what slot you're in. All sorts of problems become almost chicken and egg problems, but we've managed to unravel them and sort it all out. So one thing it does is it gives us the ability to do these orderly protocol transitions at all, full stop. That's kind of the big thing. In a way that we believe is secure, and we can run all our simulations and be assured that it's correct. But the other thing it does is it gives us modularity. So it means that we can write, as we have done, we've written the Byron ledger as one thing in isolation, and then we've written the Shelley ledger, more or less, again, one thing in isolation. And we've written those as two separate pieces. We were able to develop those two things in parallel. While we were building the Byron ledger for the Byron reboot, we were at the same time, we published the Shelley ledger specification last year. well, over a year ago now, over 12 months ago. So we were building those two things in parallel. We didn't have to build one big monolithic Byron Shelley ledger. We were able to build them in a modular way. And that will carry over into the future as well. So the hard fork combinator lets us take these separately defined ledger schemes, ledger rules, and compose them into a single ledger set of ledger rules, which can run sequentially, one set followed by the other, where we can smoothly move from the Byron into the Shelley. And then we can continue to do that into the future. So when it comes to Gauguin smart contracts or Voltaire or whatever else is coming down the pipeline in the future, it's not just combining two things, it's combining n of them, where currently n is 2, but it's designed in such a way that we can have as many as we like. So that's what the hard fork combinator is, and tune in to Edsko's talk tomorrow to get more details about that. Another little demo. This is a screenshot from a video that our colleague Philip put together the other day, which is just a quick demo showing running the nodes and demonstrating this hard fork business going from Byron mode into Shelley mode. So the demo he put together, he simply is running the nodes on his local machine. He submits an update proposal that changes the protocol version from 0 to 1. And that corresponds to when we did the change on the mainnet for the Byron reboot to move from Ouroboros Classic to Ouroboros BFT. That was a version number change in the protocol from 0 to 1. And then he submits a second protocol update shortly afterwards. We're doing this, faster than real time, of course. And that moves SES from version 1 to version 2, and that invokes the Shelley hard fork. And in his demo, which is just like scrolling walls of text, which all the best demos are scrolling walls of text, you suddenly see, now we are in Shelley mode, and you see some of the effects of being in Shelley mode, which is suddenly that slots are now 1 second long, whereas previously they were 20 seconds long. But you don't produce blocks in every slot, because that's not how Preos works. In Preos we have short slots, but we only produce blocks in on average 1 in 20 slots, so we end up with the same block rate. Anyway, so if you want to see that demo, there's a video of that, which I think we put out early this week. And we will be demonstrating the same, of course, on a public testnet in the near future, which will give everybody, including stateful operators, third parties, etc., the opportunity to see in public us moving the whole system in a testnet environment from Byron mode into Shelley mode, and people to test that things work smoothly across that, and test their own systems, if their own integrations against that. And we'll do that multiple times so that people have an opportunity to test these things. All right, let's move on to talk more about the ledger as well, and Ouroboros implementation. So, as Kevin mentioned earlier, Shelley uses Ouroboros Preos. So let me just briefly say what are the major advances that we have in Ouroboros Preos. So Ouroboros is these days, a whole family, a whole zoo of different Ouroboros, variants. If you go and look it up, you'll see there's Ouroboros, what we now retroactively call Ouroboros Classic, and then there's Preos, there's Genesis, there's Crypsinos, there's ones about time, there's all kinds, there's loads of them. But the Preos is one of the major steps. It's not like just a little feature on the side, it's a substantial revision of Ouroboros itself. And it brings with it, I think, primarily two major advances that people will notice. And these are both really security advantages. So the first one is, as Kevin mentioned earlier, that the slot leader schedule is private. So what does that really mean? So let's compare it with something with Ouroboros Classic, right, where we have a public slot leader schedule, or indeed Ouroboros BFT. So with a public slot leader schedule, that means that everybody in the system knows whose turn it's going to be in every single slot in the entire epoch. So by the time of the beginning of the epoch, everybody can simply calculate whose turn is it going to be in every single slot, and that's just known. Whereas in Preos, that is not known. It's not known publicly. So if I'm a slot leader, if I'm a stake pool operator, I can calculate, or the node can calculate on my behalf, in which slots I'm going to be slot leader. But nobody else knows that. And I can't predict, when other people are going to be slot leader, which of course has a side effect that it's possible for there to be multiple slot leaders at the same time, and the system takes that into account and resolves that kind of thing. So what's the point in that? What's the advantage of that? Why is that a security feature? The private slot leader schedule means that as an attacker, you don't know who to attack. And why is that an advantage? If you've got many like 150, or as Kevin was saying, scaling eventually up to perhaps 500 major stateful operators, if you don't know which one of them is going to be producing the block next, it's harder to do attacks like a targeted DDoS attack. If you were trying to disrupt the system, one relatively low-tech way is to kind of just do a network level, low-level DDoS targeting just that next slot leader, and you target just that one because it's going to be you saturate their network connection for the next 20 seconds when it's going to be them to produce the next block, and then you go on to target the next one, and then the next one, and the next one. So you keep repointing your DDoS attack engine. But if you have to simultaneously attack 500 state pools, and it's not just one machine, it's all of their relays, because each state pool runs multiple relays, and generally the state pool node itself is not actually on the public network, so it's only the only bits that you see are the other state pools relays, and there can be many of those. That's a substantially larger attack. Then you really have to DDoS the entire network at once, and that's much bigger and much harder for a network that is itself globally distributed. That's a much harder DDoS attack, much more expensive thing to pull off. So that's one major security advantage, the private slot leader schedule. And the other one is the key evolving signatures, KES. And this gives us what is called forward security. So what is that about? That is saying that suppose someone is able to hack into the machine that is hosting a stateful operator. That means that they will find on that machine the signing, the operational keys. Right? We operate a hot-cold scheme, but it does mean that the hotkey that is being used to sign blocks, or hotkeys, there's more than one, that's being used to sign blocks at that time would be compromised if someone is able to hack into one of those nodes. So KES is about mitigating what happens in the situation where someone is able to hack into one of those nodes. And what does it do? It says that, yes, okay, you managed to compromise the keys that are being used to sign right now, but the forward security property means that you cannot use the keys that you have compromised for right now. You can't use those keys to sign blocks in the past. You can't forge a false history. So the keys that you find now are only valid for a current period of time, and that would be up to about 24 to 36 hours maximum before now. And before that time, you can't produce false signatures. So you can't hack into a node and then use that to bootstrap an attack where you try to construct a false history. And that in itself is another major advance, because one of the big critiques, sort of theoretical critiques that people have made about proof-of-stake systems is what happens when 5 years later, you come along and you somehow manage to recover a key, or you bribe someone to give them their key that they don't care about anymore, 5 years later, and now, you can reconstruct a false history, years and years later. And that's a reasonable concern that people talk about in the papers. You can go read the details about it. But this is one way of mitigating that kind of thing, is that there's quite a short limit on how far into the past you can forge blocks. So it really severely curtails the ability to create these false histories. Okay, that's enough about Preos. Let's talk about the ledger specification, or the ledger implementation. So we, as Kevin was saying earlier, we did this in a much more formal way than was done for the original Byron implementation. And I think it's a reasonable claim to say it's really much more formal than pretty much anyone in the whole space is doing. And that formality brings us higher quality. So what is this? So, I mean, we've both Philip and I have given talks about this before. So if you're particularly interested in this, see Philip's talk or see some of our previous talks. Let me just touch on it briefly. What we've done is we've used mathematics, the language of set theory, to describe very precisely and mathematically what the ledger rules actually are. What are the rules of accounting? How do state pools work? How does delegation work? How does how do the rewards calculations work? All the rules that have to be executed by all the nodes, we have to write them down and specify them in a very precise mathematical way. So figure 36 here is it's a snippet out of a much bigger document. You see on the left, the formal spec, which we published last spring for everyone to see, and we've made a few tweaks and improvements to it since then, but it's substantially the same as what we published well over a year ago. So that's the spec. That's the intention, and we review that amongst ourselves. We review it with researchers. We review it with Charles. We review it with other people, and we publish it. We have published it for everybody else to see and to get that kind of peer review and feedback on. There's not formal peer review in the sense of being submitted to a journal, because that's not the kind of thing that they do. But it is peer review in a much broader sense of asking our peers, putting it out there in public and asking for that kind of review and feedback and scrutiny. So then we go from formal specification to an executable specification and, as we'll see, implementation. Now, it's no accident the random snippet of code we have here corresponds to the random snippet of mathematics that we had on the previous slide. Because what we do is we take that mathematical specification and we basically transcribe it straight into Haskell in such a way that you can match them up side by side and just go through and audit that they are the same. So that's our going from the world of set theory and mathematics into the world of executable running code that you can use as at least as a test oracle, or in fact what we have done for Shelley is we have used that executable specification as our real implementation as a way of quite considerably saving on development time. So if you attended any of the talks that Philip or I have given about this in the past, you'll have heard us talking about how we use testing to compare an executable specification with a real implementation. And that is what we did for the Byron ledger implementation. But for the Shelley implementation, because we didn't have a kind of legacy baggage to deal with, we were able to design the Shelley ledger rules from scratch in a way that we're happy with. We were able to do all that in such a way that we can use the executable specification directly as an entirely adequate real implementation. We just have to be a little bit more careful about making sure we get the right asymptotic complexity and the right data structures and whatnot. But we're still able to maintain this very close one-to-one correspondence with the formal specification and the executable specification, and have that be something that we can really run. In addition to that executable specification, we also do some formal proofs, and so what are we looking for? We're interested in how are we assuring ourselves that this is correct. So first of all, you've got to say, well, what does it mean to be correct? There's kind of two aspects to being correct. One is kind of sanity properties, where if it violated that sanity property, it's plainly wrong. You've plainly made a mistake in your design. And then you've got another kind of property, which is just like, is this what I want? Is this design, is this choice of how rewards are going to be handed out what I want? So it's less a question of like, is it right or wrong? There could be many right answers, but is it the right answer that you want? Is it the design that you want? So we separate those out and we say, okay, so for the questions of is it what I want, you have to do that simply by talking about it, reviewing it, reading it, reviewing it with stakeholders, reviewing it with the researchers, reviewing it with Charles and other people, and saying, here are the rules, we are presenting them, publicly, published them, and we obviously review them internally first. And is this what we really want? Is this what we want Shelley to be? So that's the basic process there, is just review, understand it, read the mathematics, read the corresponding text, and think about it. Is this actually what we want? You can also do experiments and say, here's the effect if you do that. But it basically comes down to that. And then the other aspect is, as I said, this kind of, if it violates this property, it's plainly wrong kind of thing. So what kind of properties are we talking about? The most obvious, most general one is that like money should not be created or destroyed. That's a fairly straightforward property that any accountant's ledger, no matter how complicated, ought to obey. And indeed, that's a property that we can write down, and we can test it, or we can prove it. And we have done a combination of both. So the property is the same either way, whether you test it or whether you prove it. So with formal proof, what we've done is we have taken certain key properties, right? We've not done this for everything because formal proof is more expensive, it's more time consuming. But for certain key properties within the ledger rules, we have formalized those ledger rules. We've taken that mathematics and we've turned it into formal machine checked language in a theorem prover. The particular theorem prover we use is called Isabelle. And then we have done machine checked formal proofs that certain properties hold. We don't do that for everything, as I said. It is more expensive, and we do it after testing, because you catch most bugs, in fact, by testing, which I'll come on to in a second. But then when you think you've done enough testing, you're fairly confident everything's right, then you can get that last extra bit of assurance by, for certain properties, certain key things, pulling out the theorem prover and trying to prove it and have the computer check it for you. And that's really that's the gold standard of proof. And we've done that for a few select things. And that did actually turn out to be useful. We did actually find some subtle things where it was unclear, or it could be improved, or actual bugs, which we caught by that method. So let's talk about testing, because that's actually what finds the majority of issues, and correspondingly, when those tests pass, assure us that we're probably safe from certain classes of flaw. So we use a testing methodology called Quickcheck, which is based on this notion of properties. So what sort of properties are we checking? Well, it's exactly the ones that I mentioned a second ago. It's these like balance preservation properties. But this time, we don't do it by proof, we do it by testing. So how does that work? What we do is that the Quickcheck methodology says, okay, you have these mathematical properties, you translate those mathematical properties into executable code. So the balance property is, you add up all of the pots of money in the system, add up the reserves, the UTXO circulation, the deposit pot, the fee pot, blah, 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 add them all up, and they should always sum to, exactly what the initial circulation, or the initial total value of the system was, and that should never change across, the whole execution of the system at every step of the way. And that's relatively easy to write down in code, to translate that mathematical property into a testable property in code. But you still need to test that against something. And so what we do, the Quickcheck methodology here, is to systematically but randomly generate inputs. So those don't have to be realistic inputs, because they're supposed to explore kind of all the dark corners of the input space, even the unlikely ones, especially the unlikely ones, because that's otherwise normally where you would be most likely to make mistakes. So it's random generation in this case of valid or invalid ledgers, and checking that these properties are true for all these ledgers. Some properties, of course, only make sense for valid ledgers, but some properties we're looking at, you want to be able to test them with deliberately slightly invalid ledgers to check that they are indeed detected as being invalid and rejected. And one of the really nice things about this is when it does find a flaw, it will very often be able to find the smallest or a very small example of that flaw. And that is excellent for then tracking down the problem and fixing it. So what's really good about this is that when it's done, it can generate thousands, tens of thousands, hundreds of thousands of examples and check that the properties hold. And that gives you some assurance, quite really good assurance, not as good as formal proof, but really very good assurance that you've covered the whole space and that the properties are indeed true. So one example, this is a bit of code which is writing down a property, the no double spending property, which you can write down in a mathematical way and then translate it, as we have on this slide here, into some code that expresses that property as well. So this doesn't cover the the generation part of it. This is the property that the randomly generated inputs would be expected to satisfy. Okay, let's talk about networking. So Shelley, and in particular really it's Preos, has some quite difficult to satisfy networking properties. The security and the timeliness are intimately tied up together in Ouroboros. If you can't deliver blocks from one slot leader to another within the required times, the system will not work overall. I mean, it can tolerate a little bit, but it can't tolerate failing to meet those deadlines all the time or frequently. It has those deadlines. And the real world with networking is, on the internet, the public internet is complicated and difficult, and we have to try and achieve these high levels of reliability and predictability, and do so on the public internet. And it has to be a worldwide distributed network. Of course, we want to achieve that democratic and fully distributed worldwide. We don't want it to be concentrated in one part of the world, and it needs to work with standard internet protocols. It has to get through firewalls and all the rest of it. We can't do anything too exotic, and it needs to run on ordinary people's machines. We don't want people to be having to fiddle with their firewalls. That's not the sort of thing deadless users want. So this is a hard problem, and if you want to hear more about this, Neil and I will be giving a talk about this tomorrow. Neil is a colleague of ours who works for a consultancy that what they do professionally is they tend to work with big telecoms companies, ISPs, mobile phone operators, looking at how they operate their networks to achieve higher degrees of performance and reliability, and in making economical use of resources. So he and I have got an interesting talk on this topic tomorrow. I think I won't go into detail about that aspect because I think we better cover that in our talk tomorrow. So I will hand back to Kevin.
Thank you, Duncan. Very fascinating. So I'm going to wrap up by telling you a bit about where we are, what the state of play is, what some of the future directions are, and then we'll open up to questions. So I'm pleased to say that we have already got to a stage where we have over 250 pools running on the testnet, on the Shelley testnet. So already we've achieved many times more decentralization than Bitcoin, for example. And you can see this in this diagram here. This is taken from the portal.io website. And what it shows is the interconnection between all the stake pools that are on the Haskell testnet at the moment. You can see all the connections, you can see the distribution, and you can see the interconnections. What about the future? Well, lots of exciting things that we need to do. What comes next? The first thing is we need to investigate the peer-to-peer topology to make it easier for pools to find each other. There are various extensions that our colleagues are going to tell you about to do with dealing with multi-asset tokens, smart contracts, but also new protocols, new voting mechanisms, hardware signing, etc., etc. And Shelley makes all of these possible. So it's an incredibly important technology for the Cardano ecosystem. So to conclude, many important new features in Shelley, principally delegation, distributed block production. It's the new implementation is certified correct. It's modular and extensible. It's designed for robust and scalable worldwide performance, and it's a major step to full decentralization of the Cardano ecosystem. We are going now from the federated Byron era through the hard fork to the distributed Shelley era. So thank you. Let's open up to questions.
So, okay, let me take one that I like the look of. So one of the questions here is, I'll read it out. I've heard that stake pools in Germany were getting the most rewards for some reason. Could you please explain why? Yes. So that was indeed the case on the incentivized testnet. There was this effect that we all noticed of everybody moves their server to Frankfurt. It just happened to be randomly to be Frankfurt. Why was that happening? It was because there was an incentive to be nearer to each other. It was a centralization tendency, so that you had a greater chance of winning, your slot battles if you were nearby to the other slot leaders, and so that is not a good thing, right? From our point of view, right? We do not want that kind of centralization pressure to push all the professional stake pools to end up, in one data center or one city or even in one continent. So we have actually looked at that in detail, and we have taken measures compared to the incentivized testnet to mitigate against that incentive. Now there's multiple reasons why the incentive would be less strong on the mainnet anyway, due to the performance numbers and how the network works, and as I say, we'll cover some aspect of that in the talk that Neil and I have tomorrow. We'll look at the timing and Preos calibration. But the other major reason, the other thing that we've done, the other mitigation that we've implemented, is to add more deterministic chain selection. So that says that even if someone didn't. So here's the situation you've got to imagine. Two slot leaders produce blocks in either the same slot or adjacent slots, and they're kind of racing to get to everybody, and whoever gets there first wins. Right? That's kind of the problem. That there's this then race, and you being a few milliseconds faster, and then everyone kind of moves to Frankfurt. A few milliseconds faster, and you win. So if instead we say, well, it's deterministic who's going to win between those, then there's no need to race. Right? If we just say, and this is what we do, we say whoever has the lowest VRF output, and that's not something that you can forge. The VRF is part of the Preos slot leader mechanism, and the cryptography there means that you cannot forge that. So that means that we can use whoever produces the smallest VRF, they win, and it doesn't matter whether you got there first or you got there second, and that means that will very substantially reduce the effect of this kind of everybody moves to Frankfurt effect. And if that turns out not to be enough, we will take further measures. So we are dead set on making sure that this system is properly globally distributed. Kevin, would you like to pick the next one?
Thanks, Duncan. So question from Sean is about decentralization being 1,000 times that of Bitcoin, and how many node operators do we need to achieve that? So the answer is you need quite a lot. We would expect operators on average to be running less than 2 or 3 pools each. So if you have 1,000 times the decentralization blockchain, you would have about 2,000 to 3,000 pool operators. And that in itself will prevent a single source of power, because each of these pool operators will have some proportion of the stake. So the system as a whole is naturally going to be highly decentralized. Exchanges, for example, they will have some influence, but they won't outnumber the pool operators. This is going to be a very, very decentralized system, and quite democratic, we believe.
It's worth noting that you don't need to be a lot more decentralized to be more decentralized than Bitcoin, because Bitcoin has basically only got 5 players, the 5 big mining pools. So yeah, okay, 1,000, that's a big factor, and as Kevin was saying earlier, we'll start off with 150 and then aim to scale up to 500. So saying 1,000 times more decentralized than Bitcoin is a pretty big ambition there, but I mean it's certainly far more. I mean if we end up with, I mean even starting at 150 stake pools, I mean that's already 30 times more distributed than Bitcoin, which is big. And there's diminishing returns to that, right? And the difference between 5 and 10 and 5 and 500 is very substantial. But going 500 to 1,000, it's less. There's diminishing returns as you get more and more and more. Let me pick one other while I'm jabbering on. Will exchange staking be part of the network? from the start, do you see it causing an issue with voting? So the way the rules are set up, we can't prevent exchanges from staking. They're able to exercise their rights as the stakeholders just as everybody else is. And what effect is that likely to have? So exchanges are likely to take one of two strategies. They're likely to either delegate to third-party pools that are run by other third parties, or they're likely to run their own pools, so that the money that they hold on behalf of other people is staked to not really public pools, but it's private ones that they run themselves. And we don't anticipate that being a substantial disruption to the stake pool market, but the proof will be in how it really plays out. But we've had quite a few discussions amongst ourselves and with stake pool operators and with focus groups and thought about it a fair bit, and we think we think that should work out. As for voting, so remember, of course, that Shelley will not have decentralized governance yet, right? That's for Voltaire, and the design of Voltaire is still in development, but people are very much aware of the issue of exchanges and voting. I can't comment on exactly what solution people will come up with, but people are very aware that is an interesting issue, let's say. Kevin, do you want to next one, or are we at time?
We're at time, but I think we can carry on with questions if people are happy to stay. I've got quite a few questions here, so we get to answer them if we can. So there's someone who, Dave says he's an HVAC repair guy, and is there way for someone like him to securely stash away some chips for his children, or other? Says yes, you do have to. So we've built in as much security as we can into the Cardano system as a whole, but it's very, very important that you take care of your keys. They are valuable assets like money or any other instrument. So you need to take good precautions if you're holding substantial amounts of ADA, and the precautions can include putting keys in fireproof safes, investing in hardware wallets that will keep your keys safe, making sure you always have duplicates of your keys stored securely. Some people are going as far as engraving their keys on pieces of metal and then hiding them in safe places. So there are definitely ways that you can keep your assets secure. And if you don't have the technical competence to run a pool yourself, I mean, it's a lot of fun. I'd say it's worth learning if you do have the technical competence, but if you don't, you can always participate by delegating your ADA to stake pools and by earning rewards that way. So please do participate in the system. Do you want to pick another one, Duncan?
Sure, yes, okay. So I'll take two, one about VRF keys and one about peer-to-peer. So you mentioned that peer-to-peer discoverability is something you'll implement in the future. How do nodes discover each other now? So yes, let's just say when is the peer-to-peer coming along? So the very first version of Shelley that we'll be releasing, and when we do the hard fork, we're releasing the code and then doing the hard fork, that gives us decentralization of block production. But the network infrastructure is still partially federated and partially shared by and then operated by the stake pool operators. But iWhich will initially take responsibility for running enough relays to make sure that deadless users are able to get good service. So that's still the network layer is then how the peers actually interact with each other. The graph. The peer-to-peer graph is still a kind of federated thing in the first release, and that's deliberate. We want to do these changes incrementally. So when that will come along later in the Shelley era, we still see it as a Shelley feature, and we have a team that are working on that at the moment. But it will be deployed later, and it'll be deployed smoothly and incrementally. So we'll have a gradual rollout of the peer-to-peer. So how do they discover each other now? It's very simple. It's just a configuration file, and it has DNS names or IP addresses, and so people, the stateful operators who are running the testnet right now, are already have written tools for how to manage this, and people collect these lists, and it's being automated. And the fact that you can use DNS as well means that you can have DNS round robin lookups as well. So it's being done now in a kind of manual and ad hoc way, and that's actually totally fine. I mean, iWHK will make sure there's always enough connections, but the people operating the state pools are setting up their own peering arrangements manually, and that's good. That's fine. And even after we have automation by the full peer-to-peer system, those kinds of manual peering arrangements are completely legitimate. Okay, so what was there's another question about the VRF which I wanted to take.
Put it up at the top of the questions.
Thank you very much, Kevin. So let me read it out. So since the VRF keys are fixed, they don't need to be rotated as KES keys are. If my VRF key happens by random assignment to be a low value, does it mean that my state pool is bound to lose most of the slot battles simply because I happen to get a bad VRF? Or does it work in a different way? So completely legitimate question. Don't apologize for asking silly questions. There are no silly questions along these lines. It's not simple stuff. But the answer is, yeah, don't worry, it's fine. It's not as if your VRF key will produce bad values, because the way it works is that it's random for every single slot. So your VRF might produce a low output on on this slot, but on the next slot it'll be totally different, because it all gets hashed in. The slot number and the current epoch nonce is hashed into, or is part of the input to the VRF. So it'll be different for not just your key versus someone else's key, but it'll be different every epoch, and it'll be different on every slot of every epoch. So it's completely random and uniform as to so it should be completely uniform, and half the time you would win and half the time the other guy would win, as it should be. Kevin, do you want to take the next one?
From Jared, not our Jared, I think. So the question is, can I get my tokens back if I stake my ADA in a stake pool and that pool goes offline for a long period of time or even forever? And a very important property of the Cardano system is that you can never lose your tokens. So you always retain full control over your ADA. You're merely lending it to pools for the purpose of producing blocks, and you can choose at any time to redelegate to another pool. So there's no problem if a pool goes offline for a short period, even if it goes offline forever. All you have to do is to change your delegation to another pool that is producing, and the dataless wallet will inform you of that, and it will give you a set of options, good performing pools that you can redelegate to. So it's completely safe. This is something we should emphasize. This is a completely safe way to participate in the construction of the Cardano ecosystem.
Yeah, just to follow up on that, the way I like to think about it is that delegation is not, you're not giving them your tokens, you're not giving them your value. Really, there's kind of two separate concepts. There's the value that you hold, and then there's the corresponding stake. And you hold on to the value, but you delegate the stake, and you can redelegate that at any time. So it's not like locking. There's no locking, there's no token locking going on in delegation. Let's see, another question here. My stake pool, is running with one block producer and 2 relays. Any advantage for them to be geographically distributed, or should relays be geographically close, low latency, to the block producer? I think the answer is really that it doesn't matter too much, actually, because your relays will be talking to other people's relays, and this has to be globally distributed anyway. So whether you have those in the same region as you or a different region, I think actually in the end it doesn't matter too much. Maybe I'll think about that and talk to Neil about it. But that's my first response. My first thought is that it actually shouldn't make much difference. Here's another interesting incentives one, Kevin. Do you want to take this one? I'll read it out. You can answer if you like. So the question is, if transaction fees are pooled and split at the end of epochs, what incentive is there for a stake pool to include transaction in the blocks it produces? Won't it still get the fees? Kevin, do you want to take that one?
Sorry, I was muted. So it will still get a proportion of the fees, but it's a badly producing pool, so it won't have dealt. We won't have dealt with all the transactions that have been submitted in the epoch, and that means that the pool is going to be penalised for poor performance. I believe that's correct, Duncan.
In this case, it would be that it is still producing the blocks, and so it's not penalised for not producing blocks. You do get penalised if you don't produce blocks, but I think in this case it won't be penalised in that way. I think it's much more subtle. I think it's simply that it's always in the incentive of a block producer to incorporate transactions because it increases the overall fee pool from which all stake pools, including that stake pool, get rewards. So it may be a marginal effect, but it's still marginally in your interest as a block producer to incorporate blocks, to incorporate transactions into blocks. And we don't really want to penalize people for producing empty blocks, because sometimes producing an empty block rather than producing no block is absolutely the right thing to do. Supposing there are no transactions, the mempool is empty, it's still for the security of Preos, makes sense to produce a block in that situation. So we don't want to penalize people in that case. And there is already, as I said, this marginal incentive to always fill it if there are transactions available. So we think, based on the game theory analysis, that there is always that incentive, and so we're not concerned that people would configure their nodes to never incorporate transactions into blocks.
Yeah, so let me take the question from Sean, which is, how do you evaluate a suitable stake pool operator? So obviously you could do a lot of research, but the mechanism that we're proposing you use is the desirability and pool ranking mechanism that Daedalus provides. And Daedalus will give you a list of the top stake pools. You can choose from those, and any of those pools will be a good choice. Moreover, if the pool stops being a good player, if, for example, the rewards that it's earning are dramatically cut, or it changes its rates or something like this, then the stakeholder will be notified and they can change their delegation. And they can do this at any epoch. So there's a good mechanism there to help you choose. And the desirability metric is essentially a long-term calculation of return on investment. It's the desirability the ranking metric is, it will tell you which pools are going to perform best over a long period of time based on past performance and other characteristics. So trust Daedalus or do a lot of detailed research.
Let me take another couple of quick ones here. So Ed asks, where are your tokens actually? Where are they actually held if you want to stake? Are they held in the Daedalus wallet locally or on whatever device you're using? The answer is yes, that's exactly it. When you're using Daedalus and you're delegating, the funds are held in addresses that are part of your Daedalus wallet. But you simply delegate, you point to a stake pool and say, I would like to delegate my stake there, but you're holding your funds in the addresses that are part of your wallet. So yes, they're held in your Daedalus wallet, even though you're delegating. Another question: what remains in the balance to complete? What remains in the balance for complete decentralization post Shelley go live? The answer is really two things for complete decentralization. I like to explain that there's kind of three aspects to decentralization. There's decentralized block production, and that's what you get with Shelley from the beginning. Well, as soon as we start to adjust the D parameter. Then So post go live, then there's two other aspects. One is decentralization of the physical network infrastructure, and that's what I was mentioning earlier with the the peer-to-peer, the fully automated peer-to-peer graph construction. That gets you decentralization of the network infrastructure. So that's one part, and that will come within the Shelley era, but post Shelley go live. And then the last aspect, which is in many ways the most interesting and tricky, is decentralization of governance, and that is what Voltaire is all about. So that's not in scope for Shelley. So Shelley remains with centralized governance until we get to the decentralized governance era. Another interesting question, which I'll grab if Kevin doesn't mind. The question about the block collisions / slot battles we had seen on the ITN, and we are seeing block discrepancy currently on the HTN also, missing or lost blocks. Is this because of the speed up nature of the networks or something else yet to be addressed? Probably the best answer to this will be covered in a talk tomorrow that Neil and I are giving, where in the last part of the talk we touch on the topic of how do you parameterize Preos? That is, how do you pick the parameters for Preos, like how big the blocks should be, and which really comes down to how long does it take to get blocks from here to there, which depends on a number of factors, which we'll talk about. And then we plot these nice graphs that show, for different choices of the active slot coefficient, what fraction of blocks are going to be wasted, because that is a fundamental, feature of how, or property, in some sense an anti-feature, but it's a property of Preos. Preos makes this trade-off between security and throughput and performance. It loses some degree of efficiency by losing some blocks, but it gains for that. The trade-off is for improved security by having a private slot leader schedule. So we are likely to see about 10% of blocks not making it into the chain, and that is completely expected. And that doesn't affect everybody's reward calculations. That's all just taken into account. So yes, there is some, and it is expected that there is some. Sometimes you produce a block, but the next slot leader is only 1 or 2 slots away, and it takes maybe 3 slots to get the block across the network, and that just isn't long enough. That will happen randomly, some fraction of the time, and so long as we choose the parameters to keep that inefficiency, that wastage low enough, that is good enough. And one of the things we'll touch on tomorrow, you'll see, is that there's this, you can actually, if you increase the size of blocks, you can dramatically increase the throughput of the system, but you also increase the wastage, you increase the inefficiency. So there's a multiply throughput by 10, but maybe double the wastage, and that's a trade-off that we have to pick.
Let me take the next question, Duncan. So someone said the margin is expected to be relatively low and wants to know, is there a more specific number that's shown up as the optimal level to maintain network desirability and growth? So is there a number that everybody should be targeting? And the short answer is that I've run something like 2 million different simulations, and my conclusion from those simulations is that it's a complex network, and it depends what everyone else does. So it may not be a very satisfactory answer to you, because I simply can't tell you what the optimal level will be for you. It will depend on your pool performance. It will depend on the pledge that you've got. It may depend on how much delegation you're attracting, and it will certainly depend on what other people are doing. So you'll have to monitor this and take your own decision on that. But it's clear that you will still be able to manage a sustainable level with the parameters that have been chosen. So the idea here with the settings is to avoid a race to the bottom where no pool operator can make sufficient profit to maintain the long-term stability of the Cardano blockchain, because that would not be effective for any of us in the long term, even if it worked well for a few players in the short term. So I hope that helps to answer the question. There isn't a magic number. So we've got 2 or 3 more questions. Duncan, should we just try to answer those and then
Let's do that, and then we can wrap up. I'll take an easy one first. Are epochs/slots based on the length of time or number of occurrence? I.e., is an epoch times the number of slots? The answer is very simple. Yes, slots are a length of time, and epochs are a number of slots. So therefore they're also a length of time. In the Byron era, slots are 20 seconds long. In the Shelley era, slots are 1 second long. The length of the epoch is a number of slots, which under Byron corresponds to 5 days. Under Shelley, an epoch will also be 5 days, and so it'll therefore be a lot more slots. But it's picked to be the same. The epoch length in actual time is the same, but different number of slots because the slot length is different. Kevin, do you want to take one?
So there's a fun question here, which is, will we see Cardano ADA being able to be transferred or settled without the internet in the future? And I guess Vint Cerf at this point is probably jumping up and down and saying, of course not, you have to have the internet. But the answer is, we've designed the system to work with the internet, to work well with the internet, to take advantage of its capabilities. But you can run Cardano on any kind of network, in fact. You simply need the network to be reliable enough, resilient enough, distributed enough. So you can imagine having a private Cardano network or Cardano-like network if you wanted for some specific purpose. You can imagine many different networks in future working together. So the internet is not essential, but we've designed the system so that it works well with the internet as it is at this point in time.
One little follow-up to that is that I think Charles has talked in the past about some very interesting ideas about how you might move money from one person's wallet to another without actually being on the blockchain at all, by using hardware features and some clever crypto. And essentially it amounts to transferring the private key for a UTXO entry or for an address from one person to another in such a way that both parties are assured that the person who is moving it can no longer retain it, so that it's genuinely transferred and it's not just being kept by both parties. But that relies on some clever hardware and clever crypto. So it may be possible to do things completely outside of the internet. I mean, still in the end, you have to settle bigger things using the blockchain, but you may be able to do some local transactions with people who are physically next to you by like bumping your mobile phone against theirs and configuring it in the right way and transferring the private key. But remote things are still going to require settlement on the chain. Let's see, can I take this one about stake pools? So the question is, if I'm running a stake pool and, for example, there's a prolonged power outage, short circuit, whatever, then I am likely to be penalized by the outflow of stake tokens from my pool, which has gone offline. Is there any other penalty my now offline pool will incur due to being offline? If I learn that my pool has gone offline, can I somehow relay it to a different online device in a different location? So let's see. Yes, if your pool doesn't make as many blocks as it's supposed to in an epoch, in a 5-day epoch, then indeed it will be penalized, and that means not just yourself as a stake pool operator, but everybody who delegates to your pool. That's kind of fundamental to the incentive mechanism, and that's variable. So if you go offline for a few hours and you miss a block or two, the penalty is quite mild. If you are offline the entire epoch, the penalty is absolute. You get no rewards for that epoch whatsoever, yourself and everybody who delegates to you. So definitely there's big incentive there to to resolve problems quickly. Because of course, we can't tell the difference between someone having a power cut and just deliberately being offline. So we have to penalize in both situations. But what can you do about it? Yes, you can start up a new node elsewhere and get it going and producing blocks again. Within a few hours a day or whatever, how long it takes you to do it. Or you can set up more automated, so you could do it more quickly than that. By simply moving the private keys for the or issuing new certificates for new private keys and moving those to a new node that you set up somewhere, and then you can kick off producing blocks again. So yes, it's totally possible to have a kind of more high availability setup, but you have to be a bit careful about high availability setup that you don't have them both producing blocks at the same time, because that's adversarial behavior. But as long as you can be sure that you're only producing blocks in one or the other and not both at the same time, then yes, totally okay to set things up so that you could easily switch to a different node, a different server with the same VRF key, but you could issue yourself a new KES key if you like. Okay.
Let me finish off with one question which was highly speculative, which I've answered already, which is, what about a blockchain in the SpaceX station going to Mars? Is that going to work, Duncan? Will we get Cardano funding the astronauts in the SpaceX station?
So if you mean like where are the nodes physically running, so I think Neil likes this kind of question, and he actually looked into it and crunched the numbers, and he said that you could totally run a stake pool on the moon, but you could not run one on Mars. Not with it. You could run a blockchain that was exclusively on Mars, but you couldn't run an interplanetary blockchain, not with the current timing constraints of Ouroboros. But the time to the moon, is only like I can't remember exactly, but it's on the order of a second or so, and that kind of latency, round trip times would be well within what's possible, but round trip times to ping times to Mars are just infeasible.
Right. Well, I would say that if you have a very slow rate of block production and you're not carrying much data, then you could, right? So the length of the ping isn't really the issue. It's the length of the ping relative to the production of blocks. So if you have a long enough slot time, might have to be measured in minutes or hours rather than seconds, and you didn't have data that was being transferred, then in principle it's possible. Couldn't run a Cardano stake pool on Mars with the current settings. We could run one on the moon, as Neil is saying. But if you think of some future version of Cardano, then perhaps you could. So Cardano on Mars, how's that for an ending? Okay, thanks Duncan, thanks everyone. Great to chat to you. Hope you've enjoyed yourselves.
Thanks everybody. Thanks for all the good questions.